Can you see the slides?
No, ma'am.
No, ma'am. So just already shared. Now can you see?
No, ma'am.
No, ma'am.
What happened? It's only shared, right? Right. Can you see now?
No, ma'am.
Like maybe like it will take some time to
Okay.
come.
Okay, just
Yes, ma'am. Now it is coming.
coming, right? Okay, good. Um, so far we were discussing about the modeling techniques. If you just recap a bit, we have started our discussion with finite state modeling. So finite state machine, there we have seen how we can map our specification to different states, and then how we can connect those states with some transition conditions that will entirely give some idea about our specification. Then we have identified that there are some limitations in FSM, and for those, like we have added some the concept of added variables, and we define extended FSM. We added the concept of hierarchy, and to actually make of our complex specifications more clear, more properly representable. Then we have seen that at a time when we are moving towards our complex requirements, at a time it is not that only one FSM is running or active. So multiple state machines can be active at a time, and that's why we have talked about the concept of concurrency. So that way, in the state chart, starting from FSM to state chart, we have talked about different complex specifications. We have added different complex specifications, complex possibilities in FSM. Then what we have seen, we observed that there are some limitations in FSM after doing so much. In spite of the fact it is quite clear, quite important, expressing our event-driven scenario, event-driven specification, there are still some limitations. Like one limitation is not so much things, so much state transitions. That part is not required when we are talking about entirely data intrinsic models. When we are talking about some data related filtering, data tuning, those type of scenarios. So for that, we talked about the data models. Then we talked about another limitation of FSM, that is FSM, or better to say the extended or hierarchical FSM, that is the state chart state chart uses the concept of shared memory, and that is not suitable for distributed scenario. For that reason, we have talked about some other type of modeling technique, that is SDL, specification description language. So these are what we have talked about. Okay, we've also talked about TEFINIT, where we are in concurrent scenario. In our specification, if there are different concurrent paths, synchronous paths, and we have to handle everything, that time more prominent modeling technique what we have seen, that is the TEFINIT. Now, whatever we have discussed, if you now recap or think a bit, you will see if your scenario is like this, you have multiple processes, and those processes are exchanging multiple messages between them. That modeling, the scheduling or visualization of those messages, this part is not actually covered in many of the models. Like even this part, the multiple huge number of message exchange is itself a problem when we talked about HDL. If you remember one limitation or one complication of HDL, what we have identified is that the use of message queue. That is the advantage, the use of message queue in case of distributed scenario. That's why HDL was popular over state chart, but that is also its limitation, because beforehand designing the size of that message queue is itself a problem, because for that you have to know what number of signal exchange or message exchange is actually taking place in your, when your system is running based on your specification, whatever you are given. So those type of particular modeling scenario requires something extra that will give you some idea about how to handle the scheduling of messages, or how to visualize the scheduling of messages. So today we are going to talk about one typical modeling technique, that is message sequence chart, which gives that idea. So this is a bit theoretical, some points. Before that, this is how it looks like, how we can interpret or we can actually visualize the sequence or scheduling of messages in message sequence chart, MS. So here you can see there are different, that this MNC is mostly based on event ordering, but one limitation that we will come next. First, you understand that there are multiple processes going on, and they are exchanging messages between them. Now, what MSC does is it actually represents those messages. Like this M2, it is generating from this process A, and it is it is destined for this process B. So that way, what are the event or what are the signal exchange is taking place, that can be interpreted by this message sequence chart. So there are different symbols again. This is the starting of the process, this is the end of the process, and it signifies this message is only valid within the lifetime of these two processes. And there are some other symbols are also present, that is, if messages are lost, this type of symbol, messages are found, this type of symbol. If this message is actually going from one process to another based on some condition, then within this type of symbol you can write some timer is also associated with how much time this message is valid, or to represent within how much time this message will send from sender to receiver. But there is a typical limitation in this message sequence chart. First, it is too simple, and the second part is, if you see this M2, M3, M4, these are written in this way, but that doesn't mean these are ordered in this way. That means MSC only tells you that what are the number of messages going from one process to another, and what is the originating process and what is the ending process. But it doesn't give any idea about the relative sequence of these messages. That means this M2 and M3 drawn in this way doesn't mean that if M2 is getting, you have to send M2 from process A to process B first, then M3 will come. No, this type of idea cannot be, this type of intuition cannot be developed by MSC representation. So this is one of the major limitation of MSC, that it only gives you the idea of messages, number of messages, but it doesn't give you the idea of precedence. So this is one example where in ATM withdrawal example, where there are different message exchanges takes place from user, ATM, bank. So when you are actually developing them in some distributor scenario, you are actually developing separate modules from user, ATM, bank, and they are going to communicate with some message queue. So advantage of this MSC is that you can actually, for a particular period of time, you can actually get some idea about how many number of messages can be exchanged, and that may give you the idea that how you can, what is the maximum worst case size you can actually predict for that ACL message queue. So these are typical very limited usage, limited advantage of MSC. So a better representation of this type of message, visualizing this message sequences, called how tasks are connected, how tasks are dependent based on some message exchange or signal exchange. So this process network or task graph is a better representation in modeling. So you can understand that by this diagram that there are multiple tasks, T1, T2, T3, T4, T5, and T1 is sending some input to T2, T1 is sending some input to T3, T3 is sending some input to T4, and so on. So this is typically, without any other extra information, it can be considered as a dependence graph, that is a directed graph, okay, in which you are defining the edges and their partial order. So from this you can get the idea of immediate predecessor and the successor of these nodes, and what are this precedence relation between different signals, okay, from where it is generating. And now maybe from these tasks you can get some idea. For this task T2, you need to have some input from T1, and from T2 again some output should be gone to T5 for completion of execution of T5. That way the precedence, that dependence can clearly be understood. Moreover, in case of embedded modeling, this task graph was actually extended with some timing information. Okay, this timing information signifies arrival time, and of course this is the execution time, that is start time and the execution. So it also the extensions of this task graph also give you the idea of how periodic schedules can be done, and hierarchy can be introduced in this task graphs. Like this T3 and T4 will be executed in a particular level, and then this T1, T2 and T5, there in the output will be sent to the next level. So that way, when we already have seen that how this hierarchy, introduction of hierarchy is important, and that's why we moved to hierarchical FSM in our FSM discussion. So those logics are similar, only this hierarchy is again introduced in this dependency graph concept, and this task graph with the addition of this timing details, with the addition of this periodic details, with the addition of hierarchical details, is what do you say? Is an improvement over dependency graph that is more suitable in modeling this task scheduling scenario of complex cyber physical system or embedded system. So these are the typical modules, whatever we have discussed, like starting from FSM, then PET-FINET, then LCL. Whatever we have discussed, basically, we will see the other and the final modeling technique that we will name, that is UML, Unified Modeling Technique. Here we will see that whatever we have discussed so far, whatever knowledge now you have about these different modeling techniques, those are amalgamated, those are combined together under the same roof in the form of different packages. So why it is required? See, when we are starting with some modeling technique, like when we talked about FSM, we told that, okay, FSM is suitable for some event-driven scenario. When we talked about data flow model, we told that, okay, it is for data intrinsic purpose. But when you are getting some specification or someone is actually developing complex scenario specification, like we talked about a complex V2I scenario, vehicle to infrastructure scenario nowadays, that is the ultimate concept, multiple development in automobile domain with the cyber physical concept, where your vehicle will not only based on sensors, will not only your vehicle parts, marker parts will be communicating with each other. The vehicle will communicate to the roadside traffic light controller. Vehicle will send and signal to the pedestrians. Vehicle, driverless cars or driverless automobiles, they will detect through some sensors whether there is some pedestrian or not in the in the crossing, and based on that, the car will move or stop. So here in this case, it is not only that some event-driven processing. Sometimes it is data intrinsic processing. Sometimes it is event-driven processing. Sometimes there is concurrency. Sometimes there is synchronous situation handling. So everything is there. So when these type of complex scenarios are coming into picture, it is always not possible to understand beforehand that what modeling technique I will use. That precise knowledge or behavior of the system may or may not be present beforehand. That's why UML is a so popular concept which provides different types of packages. Now, if we actually talk about those packages, you will see whatever concepts we have discussed before in this previous all this modeling techniques, basically they are under the same roof, nothing else. So there is one concept, basically when UML was first proposed, it was not meant for such type of cyber physical scenario or embedded scenario. It is a general modeling technique, and generally after UML 2.0 version also, it was evolved with some event-driven scenario, with some added features, I should say, to be suitable for this embedded or cyber physical system modeling. Okay, now we can see what are the different types of space packages as present. Just quickly, I will give you another presentation. You can go through it, how they are defined. But just to give you the idea that, see, first the sequence diagram. This is same as whatever we have discussed in the message sequence chart, where we are having some process generators and some what are the sequence messages are getting exchanged. So this is a variant of message sequence chart. Then the state machine diagrams or state machine related package. So this variation also includes whatever you have, whatever we have discussed in state related concept. Okay, that is basically the hierarchical or concurrency related state machine. Okay. Next, the activity diagram. Activity diagrams is mainly made for handling those concurrency and so on, and that is mainly the concept of extended faithfulness. Okay. Similarly, the deployment architecture, these are basically execution architecture. This is mostly related to, we will come after this when we have the idea of modeling, how we are mapping them again to our execution architecture. So this is basically for in the deployment part, actually in the implementation part, how our modeling technique is getting deployed in the execution architecture. So something related to that, adding OOPS concept, I mean the object-oriented concept, the class diagrams, some use case diagram, and other, so with the concept of hardware and software partitioning of the software and hardware packages. So whatever different diagrams you can see in UML, those are just representations, and you can see those are basically the combination of what existing modeling techniques was in literature, and a bit something extra like timing diagrams. Those are always there in mapped with different separate modelings, and here separate diagram technique is given for to, and that is mentioned as a timing diagram. And next one, the last one, very important one, that is the communication diagram. Communication diagrams, that is representing the relations between the classes and the messages that are getting exchanged. So these are the different packages present in UML, and the main idea of UML is that you are basically combining everything under same roof. So I will again share a separate slide. I can show you. Okay. So this is one typical slides, a few typical slides of how you can actually write those UML class diagrams, UML, how you can define those use case diagrams, what are the nodes and what are the terms related to it. So I'm not discussing them in the class. Those are too trivial, I think. So you can go through it and you will find that the whatever we have discussed as a concept, those things are basically added as a package there. So if you are interested, you can go through it. This is just how it is represented in UML language. Okay, this is the state chart diagrams for objects. You can see how the dynamic behaviors of those objects are actually represented in UML language. So I will share that these slide also with you. You can go through it. Okay. So this is what we have discussed all about our modeling technique. Okay. So in modeling technique, is there any question so far? Let me ask. Is there any question or any part? Just let me know. I mean, if you want to. Oh, sorry, I've not started the recording. Okay. Any questions so far? Go through those different types of modeling technique so that you can understand that in which case you have to use which type of technique. Now this is okay. This is one reference. This book is also shared in your drive. You can go through it. There, other than lease Asia and that initial part we have discussed from the other, mainly we have discussed from that lease Asia book, And also the last few modeling techniques, simpler modeling techniques, we have taken from this book. So that is also present in the drive link. You can go through it. So now we have understood, I think, what are the typical different modeling techniques we should actually follow when we want to better understand the specification, our complex specification. Now we will again go back to our first day slide just to get our understanding clear that what we have discussed and actually where it is, where this modeling part actually affecting. Okay. Sorry. So again, we are coming back to this basic, our mother diagram. We have seen basically we are interested in developing these typical computation units, our embedded controller units. Now, probably when Professor Shomnath here has discussed, you got the idea how you can develop the notion of controller part and what you have to understand for that controller part to map that to your computation unit. And then probably some design step has been discussed to you. And here we have talked about the modeling part. Now, once the modeling is done, this is like something this. You have different blocks in your module. It may be some FSM blocks. It may be in your PET-PNet. You have defined some event, and based on that, there are some change of tokens. It may be some operations mentioned in your data flow model, and those operations you are actually applying your input data stream and you are generating output data stream. That module may be coming from your SDF model, where from your start state to your end state, there are different transition conditions you have to execute and you have to get the output. So whatever may be, you have got how you are actually arranging your components, and if those components are, talking to each other suitably, your modeling technique is giving you the idea, okay, you can actually implement your design. Okay. Now you have got like this. You have got one component or one block that now you have implement. Basically not one block, you have to actually implement multiple such blocks. So remember this example, we have started with this example. I'm just recapping this once again, that whatever we have understood from our modeling technique, now we have understood, we have getting a clear picture, clear idea or clear arrangement of components to implement this maybe mother block. Or maybe now you can think this is a sub block that you are going to implement. For that, with your FSM technique or maybe some other techniques, you have written within your FSM block, you have written some C code, right? Now you know how with some concept of hierarchy, concurrency, you are going to arrange multiple such blocks to get your specification idea. Okay. Now we are again coming back and concentrating on a single such code block maybe. Now we know that for this code to implement, what you have to do, you have to focus on this each and every operators. What operations you want to do, and that operations basically defining, if you remember that we have already discussed your data path. That means what operations what you are going to do, and those instructions you are writing one by one. Now through your modeling technique, you have basically either clustered these instructions or optimized these instructions, or you have actually arranged these instructions properly in some blocks so that either it can run in some hierarchy or it can run in some concurrency. But whatever you have to do after the finishing this modeling stage, again you are coming back to this design stage and you are dividing your operations. You are trying to implement your operations on some process. For that, again, the same thing, that you are either going by instruction, you are just writing the instructions and everything is taken care by your processor. That is your general purpose processor that you have. You can maybe, again, we can go back to this diagram now. You have everything ready, your program memory, your register file, where you are storing your instructions step by step, and you are fetching those instructions based on the operations. You are sending them to your arithmetic logic unit, and your arithmetic logic unit, based on your control logic, whatever instructions you have written, they are basically executing in sequence, right? So in general purpose processing, that we have already discussed before, that we are only arranging the instructions. That's all. That means we are only working in the software part mostly, and that's why we are only focusing on the instruction writing. And that's why, I mean, for this course or whatever we are developing, we are telling that we are developing embedded software. We are not telling that we are talking about fully embedded system design, because in most of the cases we are just writing the software part. That means you are just writing the set of instructions. But in case of application specific processes, you know that all the instructions are not present. It is not that any specification you take, you will actually can map to this application specific processor. And that idea will come from your modeling technique. Your modeling technique will give you the idea that what type of instructions are required for better implementation of your model. For example, when you are actually implementing some data flow models, you have modeled during your modeling stage, you have seen that these are just some filtering operation, and you have just restricted yourself for that operation some operations that can be done only by some DSP processes. That means some mathematical operations. If that's so, you know, now I can implement my model, my specification with one single DSP processor. The advantage is that with that processor, maybe I can get a better output, better performance compared to this general purpose processor. Okay. Again, your modeling technique, it means give you the idea, you know, whatever your specification is there, that requires maybe one or two single operations, maybe some addition or multiplication. That's all, nothing else. In that case, there are two options you have. In that case, whenever you are implementing, you can think, okay, I don't care about the performance, I will go to this general purpose processor. Why? For general purpose processor, like doing a soft code, everything is ready. I will just add the instructions, write instructions step by step, and whatever output I will accept it. But think about embedded scenario. Whenever you are going to this process, it may happen this general purpose soft code related technique, it may be whatever performance it is giving, it may be maybe it is not suitable for your real-time requirement. That means that to perform those addition and multiplication, actually here in this course we cannot discuss about instruction set architecture and that other features present in your processor, like pipelining, like memory organizations, how your memory is talking to your arithmetic logic unit, what is the speed of that. All these features come into picture. So for this reason, whatever maximum performance you can get in your general purpose processing, it is restricted and it cannot go beyond a particular limit. That's why it is based on your real-time requirement whether you can always take the easy path of accepting this general purpose processing and writing few soft code, or you have to move to some single purpose processor. Single purpose processor means basically hardware design. That means you are efficiently designing those added, those multipliers, and you are maybe designing a small memory. That small memory may be interacting with your arithmetic logic unit in a faster way so that your overall computation performance is improved. And maybe you are arranging, scheduling your task in a parallel way so that in your single purpose processor may give for that very restricted operations may give huge performance improvement that is not possible in your general purpose processor. And sometimes that performance improvement is mandatory based on our real-time requirement in our embedded system scenario. That's why these choice of processors are important. That maybe we have just quickly touched in our introductory discussion, but it is important to understand. And from that modeling technique, we have to again come back to, it will give us a clear idea what components, what type of memory organization, what type of processor I can actually use, so that ultimately the purpose for which I'm developing this embedded system, that speed, that resource requirement, everything can be matched. And based on that requirement, I have to choose my processors. Okay, so this is the basic idea why modeling is important before going to any implementation step. So based on that, I will take either general purpose or specific or application specific processor, and whatever processor I'm taking, it should have these three, either I'm taking or I am developing. It should have this arithmetic logic unit, the memory where you are storing, and the control unit. This is the basic structure of system architecture. Because this memory unit is storing what instructions you are actually going to implement. Arithmetic unit is actually implementing that. And in arithmetic unit, which part will get activated and which flow should be taken, and when you will actually communicate with this input and output device, that part will be controlled. So that's why this is the basic idea of what you are actually designing the embedded system architecture. And when you are designing those system architectures, or when we are actually designing embedded controller or embedded software, which part you will focus. Now, this is not all. I mean, when we actually developing some software or developing some controller, implementing some controller, of course, here the critical part is doing the timing analysis, right? Now, for that timing analysis, again, I'm telling some features of your backend system architecture will actually affect. That is your memory, that is what type of parallel property your processor is actually supporting. So those are typically some detailed discussion that we are not doing in this course. But just always remember that when you are moving from modeling to implementation technique, first thing, you have to write those set of instructions, but it doesn't mean that the set of instructions, the efficient writing of the set of instructions will only give some desired amount of timing requirement. It is dependent on different factors, and one major factor is how you are arranging your instructions and what type of supports you are getting from your backend processor. Both these two important factors come into picture to decide your execution time of your embedded software or embedded controller. And I think by now you understood that that is the most critical part. Whenever you are designing in any embedded controller or embedded software, that is the most critical part, whether it is actually satisfying your real-time requirement or not. Yes, any question? So again, this part we have, I'm not going again to this part. This part we have already discussed that if that that real-time requirement is not getting satisfied, I think this part also discussed by Mr. Sharper that we are defining our specification, this system analysis. Sorry, we are in our from the specification we are coming to the system analysis, and when in our modeling step itself, when based on our component performances, we are getting the idea that whether these components can be merged together to satisfy my implementation requirement. And then maybe based on the timing requirement, if we see that when I'm choosing this processor P1, processor P2, and the combined effect will not give the timing, satisfy the timing requirement, then what we are doing that we are dividing them to software and hardware path. So that idea also I'm getting from my modeling stage, whether I should go for a quite simplified fully software design, or I will break my design to hardware and software part to match my timing requirement. Okay, so this is the idea of that maybe we again discussed that sometimes we implement in the CPU part and sometimes we divide in the CPU and FPGA part. So for hardware and software requirement. 1 second. Okay. I think you have by now you have also the idea that whenever you have designed this coming from modeling to implementation, you have completed your implementation for a particular task. That is not all. With these multiple tasks may run on this operating system. That is basically the set of instructions that is scheduling that what processes will get executed and which way. And in your real-time operating system, I mean, in scheduling, when you have seen that maybe you have already learned different types of algorithm, RMF, and other type of real-time algorithms, then you have seen that how these type of multiple processes can be scheduled in your operating system, and your operating system should be able to take care of schedule your task, maintaining that real-time requirement. So that is one another important aspect of embedded software design or embedded system design, whether this real-time requirement is real-time operating system is capable of handling that real-time algorithms, scheduling algorithms, and whether that processes can be, I mean, arranged in a suitable way to match your real-time requirement. Okay. So this is finally then the ICE technology. I'm not going this, we have already talked about it. So following this model, basically, now we know that we have some requirement, and from there we are doing this requirement analysis, and from there we are coming to this system and performance modeling. This performance and system modeling we have discussed in detail, and we have checked that what type of different modeling techniques can be applied for different types of specifications. And then from this modeling technique, we are getting this idea whether I should go for the software design or hardware software requirement. And then finally, after the design is complete, implementation is complete, then we are moving to this part of testing, right? So this is all about how we are actually developing, you are actually developing the embedded controller design on single embedded controller design. Okay, but the challenge is maybe I will just give you a bit introduction today. From next day we will start that when we are moving to that actual complex scenario of CPS domain. It is not that we are only talking about one single embedded system design. We are thinking about how these multiple embedded systems, embedded components may communicate with each other. For example, we can come here. If you remember in our introductory class, we have talked about this. Now you can better understand. Maybe that was your first class. Now I think you can better understand that so far we have talked about designing these type of CPS nodes, single cyber physical nodes, single embedded system nodes, and they have their specific purpose. For them we have drawn some modeling technique, and for them we have taken some implementation strategies, and we've implemented on some processes. Now we have to move to this path. Next, we have to develop some CPS units where multiple CPS nodes can be combined. And then these CPS units may be combined to some CPS systems where these CPS units may be located in a what to say, in the same location or maybe distant location, and maybe they are communicating through some sensors, through some internet. So these type of distance communication, maybe some physical communication or maybe some distance communication. So for that, you understand now that these components are different. Their input output ports are different. The protocols they are following, everything are different. And to handle them for their communication, we need to know multiple communication protocols so that these nodes can actually communicate to each other to form a CPS unit, and then again these CPS units, they can communicate with each other to form the CPS system. For that, a few communicating techniques, maybe those are depending on your requirement, they may be serial, they may be parallel, and they may be they may be physically connected, they may be network based connection. So there are different types of embedded communication protocols that we are going to discuss from next day. We will be starting our discussion on that embedded communication, and so there we will be mostly focusing. First, I will give you some overview of what is the requirement of embedded communication and what are the challenges and what are the different error handling techniques, etc. But the few direct communications we will be talking about, and one detailed communication we will be talking about, that is the CAN protocol. Because if you see this diagram, this is our present automobile communication requirement they have shown. So here you can see that if you now follow that backbone part, that is communicated by Ethernet. Otherwise, this FlexRay and CAN, this communication strategy is a very prominent one in present automobile, in different CPS scenario. Here you can see powertrain and gateway communication, body gateway communication. All these cases, this CAN communication is very important. So that's why we will give the detailed idea of how CAN works, and then what is the improvement of FlexRay? I mean, what added slots are there to handle this, what to say, real-time requirement? That is a main challenge in embedded communication. What are the extra features that is added in FlexRay? And so these comparisons we will discuss. We will start from next week. Okay. So is there any question, or do you want me to repeat some part?
Ma'am,
Yes.
during this course, do we have to tackle the designing process any time in the future?
Pardon? Can you repeat the question?
Like during this course, do we have to tackle that designing process, like modeling in some software kind of thing? Do we have it, or just it's just the theoretical part we have to study?
See, in this course, this is a theoretical course. Okay. But of course, if you are actually, we are having a lab, embedded software design validation lab, but that is not a part of your coursework. But of course, if you are interested, next day I will give you the link or some idea of the software that you can use the actual modeling, and I will give you some link of the examples, okay, where you can see that how this typical starting from some specification. Like for example, we are already designing in our lab, like one example I can say recent, that traffic light controller. You are having traffic lights in a one center point maybe, and some multiple sub lanes. So when you are designing this traffic light controller, you have to take care of the traffic movement of that center, also with the sub lanes. So those are basically is a problem of hierarchical and concurrent FSM. So this is maybe you can start with some smaller examples and you can move to this. And so how you can actually model that to some specifications. So if you are interested, of course, next I will give you the link of that software. How you can use it, and some examples that will give you the idea how you can model your specification and see the outputs. Okay.
Okay, ma'am.
But that is not the part of this coursework. Okay.
Okay, ma'am.
Okay. Anything else?
Can you mention the name of that software you were telling?
Simulink.
Okay, Simulink only.
Yes, Simulink.
And regarding that chip design, anything?
Okay, chip. See, when we do that chip, basically there are two things. This is the modeling part, and next comes the hardware part, software and hardware design. Okay, this software design, we can use that embedded C. With the C code. You remember we have taken one example of, we are modeling that FSM, and within that FSM block we are writing some C codes and we are executing.
Yes,
so that can be handled by, you remember, right? Yeah. So that part can be implemented by embedded C. Okay. And there are two parts. One is, if you concentrate on the hardware software design, then the hardware design mostly, if we focus on that FPGA design. Okay. This FPGA design, for that there are few languages. The one is Verilog, one is VHDL. Okay. So that Verilog, what we do basically, that those languages, those are called hardware description languages. Basically, the way we write C, exactly that is not the same way we write the hardware description languages, but that is very similar. What we understand that hardware by blocks, so they're a bit different technique, and then we write them, right? For example, maybe one counter. You are remember, we in our traffic light controller we have added one counter. That counter, it will go up to 60, and then maybe some state transition will take place. So if you are going to implement that in a hardware, so how you will write that in some hardware description language? So there are different languages like Verilog, HDL, and those we write and run some hardware platforms. That means there are one I can name, like there are many actually. Xilinx based platforms, maybe there are Vertex platform, Vertex 6, Vertex 7 nowadays. So on that that platform, that is your processor actually. On that you are coding and you are actually finally implementing. So when we go for that type of implementation, this microprocessor based software implementation is quite easy because that processing is totally done for you. You are just writing the set of instructions. But when we are moving to that hardware implementation, we write those hardware language based codes. And another extra step we have to take care of, that is the routing, right? That means you are actually moving to the hardware now. You are having some components, and how that components, one input is actually connecting to the other output. So that overall performance should be taken care with the considering the routing or communication technique between the components. Okay, so that parts, I mean, that those are actually, that is another typical discussion. So all these parts need to be taken care of when we use of the hardware design. So if you are also interested in hardware design or FPGA based design, so Xilinx, you can follow Xilinx based softwares. SDK is there, and there you can choose your related maybe Vertex 6, Vertex 7 platform, and you can download or design and you can check. So that way, typically those are the typical tools. Okay, so actually whenever you are doing the micro specialization or full micro, because this is a foundation course, those who have taken this as an only as a what to say, just what to say, optional course or something like that. So for them this is just a theory course, but those who are actually doing the as a full micro specialization course, so we will be taking after this next semester, next to next semester maybe, we will taking those tabs, or we will be assigning projects where actually you will get acquainted with these tools. Okay, but not in this semester. So maybe it will start from next to next semester for those who are actually going for that whole full micro specialization. Any more questions?
Thank you, ma'am.
Okay. So that's all. Otherwise, you can leave now. So we will start to talk about embedded communication next day. How different CPS nodes can communicate and all.